Hello guys, welcome to a new lecture about probability and statistics. In today's lecture, we want to study discrete random variables. Let's start with random variables first. Imagine running an experiment. For example, flipping a coin. The sample space is simply all the outcomes. So S is equal to tails and heads. A random variable that we abbreviate like RV is a rule that assigns a number to each possible outcome in the sample space. It has a domain, and the domain is simply sample space. And the range of the random variable is real number. In here, we use uppercase letters like X and Y. For example, we say XB1 for heads and XB, for example, 0 for tails. This is super useful in coding when we need to quantify random events. So in this figure, you can see random variables of an experiment. So we can, this is S sample space, and we assign each outcome to one real number. The name is confusing, random variables, because it's not random, it's not variable. A random variable is a function. It's a function that maps element from the sample space to R. So we can say S to R. This S here is sample space, all possible outcomes of a probabilistic experiment. And the function X assigns numerical values to each possible outcome. For example, you roll a die. If we may get 1, 2, 3, 4, 5, or 6. So we can define a random variable here like X. We say, for example, X is equal to 3, X is equal to 6. This X here is not itself random, but deterministic function, and it assigns numbers to outcomes. Random also is confusing here. Although it has random in its name, a random variable itself is not random. The randomness comes from the underlying probability distribution that governs which outcomes occur. The sample space here contains all possible outcomes of an experiment. And then the probability measures like P assign probabilities to these outcomes. And the random variable X simply maps these outcomes to real numbers. Also, it's not variable. In algebra and calculus, we define variable as an unknown or a placeholder for fixed value. For example, we say x is equal to 5. However, in probability theory, a random variable does not have a single fixed value. Rather, it presents a range of possible values based on the probability distribution. In a single trial, the random variable takes on a specific value. Across multiple trials, the value changes according to its probability distribution. So in summary, a random variable is a function that maps sample space outcome to real numbers. It's not random. The function itself is deterministic. The randomness comes from the probability distribution. And unlike algebraic variables, it does not hold a single fixed value, but rather describes a probabilistic process. Let's see an example. A student calls a university help desk. There are two outcomes, success or fail. We say S if they get help right away, or F if they are put on hold. So we have sample space S and F. We define a random variable like X, where XS is equal to 1, it means success, and X is equal to 0 is failure. So this is a simple scenario of yes or no scenario. Random variables come in two flavors: discrete random variables and continuous random variables. Discrete random variables have countable values like 0, 1, 2, and so on. Think of the number of bugs in a code. On the other side, continuous random variables cover all numbers in an interval. For example, time to run a program. They are trickier because no single value has positive probability. It's all about range. So once again, discrete random variables whose possible values either constitute a finite set or else can be listed in an infinite sequence in which there is first element, second element, third element, countably infinite. On the other side, continuous random variables whose its possible values consist either of all numbers in a single interval on the number line, like for example from minus infinity to plus infinity, or all numbers in a disjoint union of such intervals, for example 0 to 10, right? Or you can say 20 to 30, and you can say union of them. A random variable where there is no possible value of the variable has positive probability. We can say, for example, probability of x is equal to 0 for any possible value because it's continuous. Today, we are focusing on discrete random variables, which are easier to handle in algorithms and simulations. Let's look at an example. We test married couples' blood until we find a pair with the same RH factor. This RH factor, or full form is rhesus. This is a kind of inherited protein found on the surface of red blood cells. So if your blood has the protein, your RH is positive. Otherwise, it is negative. So let's X be the number of tests. And since we test two people at the time, so X is always 2, like 4, 6, 8, and so on. This is the domain. This is the domain of our random variable. And this is discrete because we can list the values. In other words, since the possible values have been listed in sequence, X is called as a discrete random variable. Let's talk about probability distribution. For a discrete random variable like X, probability distribution tells us how the total probability, that is 1, splits across its values. So in here, we use something called as probability mass function, or in short, you can say PMF. This PMF provides the probability for each value of the random variables. In other words, for every possible value of X of the random variable that can take, the PMF specifies the probability of observing that value when the experiment is performed. And PMF gives the probability of each X values. Two rules we have here. This fx PMF is always non-negative. It means it's equal to 0 or more than 0. And always sum of all PMF is equal to 1. Think of it like distributing 100% across outcomes in a game, right? So fx is always non-negative, 0 or positive, and sum of all fx from 1 to n is always equal to 1. Try to better understand the topic using an example. Imagine a lab with 6 computers. X here we define as a random variable, and it's the number of those computers that are in use at a specific time. So in this table, the probability that no computer is in use is 5%. The probability that one computer is in use is 10%. The probability of 2 computers in use 15%, 3 25, 4 20, 5 15, and 6 10. You can see here X, the first row here is the possible X values for our random variable, and the second line PX, PMF, is the probability of each such value. Now, we want to calculate the probability of interest using elementary probability properties. For example, the probability that at most 2 computers are in use, at most 2, it means X is equal to or less than 2 at most. It means X is equal to 0, X is equal to 1, and X is equal to 2. This one, and this one. So we sum up them together and we get 30%. The probability that between 2 and 5 computers are in use, right? In this case, we go for 2 to 5, both 2 and 5 are included because greater than or equal to 2, less than or equal to 5. So this one will come to here, this one will come to here, this one will come to here, and this one will come. You sum up them together. So the probability that between 2 to 5 computers are in use is 75%. Here, let's talk about the parameter of the distribution. The possible values that the quantity can be assigned to the collection of all probability distribution for different value is called as family. Distribution often depends on parameters, like numbers that shape them. For example, a parameter might be the success probability or sample size. Changing the parameter gives a different distribution, and we call it as family of probability distribution. Think of it like tuning an AI model. We tweak the setting, we get different predictions. Suppose we observe birth until a boy is born, right? X here is the number of births observed, and we assume that the successive births are independent. So you know that we have two possibilities, girl or boy, right? So the probability here is equal to 0.5. 1 by 2. Px is equal to 1 is equal to P is equal to 0.5, right? Px is equal to 2 is equal to Pg, girl, and boy, right? And then we say P girl multiply P boy, 50%, right? This one is also 1 minus 50%, 50%. We get. And the same, for P equal to 3, we go for this one, right? Px is equal to 3, girls, because we are waiting to get the boy, right? Eat new protein at a certain until we get boy. It means whenever we reach to boy, so when it is 2, so it means the first one was not a boy. The first one was a girl, second one was a boy, right? X is equal to 3, it means the first one and second one was girl, but the third one was boy. So probability of girl, probability of girl, probability of boy. Again the same, and you will get 125%. By continuing the same for 1, 2, 3, and so on, we can find a general formula. We can say Px is equal to 1 minus P in power of x minus 1 into P x 1, 2, 3, and 0 for otherwise. In here, the parameter P can assume any value between 0 and 1, right, based on the equation that we have. This is a geometric distribution waiting for the first success. It is useful for simulation like how many tries to crack a password. We will study it in more details later. Now we are ready to learn CDF, cumulative distribution function. The cumulative distribution function, CDF in short, this adds up probabilities up to a point. Adds up probabilities up to some. For some fixed value like x, we often wish to compute the probability that the observed value of x will be at most x. For example, let x be the number of beds occupied in a hospital's emergency room at a certain time of day. So probability of 0 occupied is 20%, 1 occupied 25%, 2 occupied 30%, 3, and so on. And here, so this is our x, and this is PMF, right? Here we say x less than or equal to 2. For x less than 2, we have to sum up this 3, right? This 3, and we get 0.75. And similarly, for x less than 2.7, right? Same, because less than here. For x less than 2.99, also same, up to here, right? In here, if I want to get px less than 0, it will be 0. But for x less than or equal to 0, it will be 0.2, right? And for px less than or equal to 4 is all of them, which is equal to 1, sum of all together. So it's like a running total. Great for answering, for example, what's the chance we are at or below this level. It's resource planning. So this one way we can say it's kind of running total. Formally, the CDF or Fx, we write by capital F, is the probability that x is less than or equal to x. For discrete variable, it's the sum, right? For y less than or equal to x, py, sum of them together. It's a step function, jumps at each possible value. Let's see one example in this context. A store carries flash drives with either 1 gigabyte, 2 gigabyte, 4 gigabyte, 8 gigabyte, or 16 gigabyte. This table we have here, and y is the number of memory in a purchased drive. So 1 is equal to 5%, 2 10%, 4 35, 8 40, and 6 10%. CDF of y is y probability of y less than or equal to 1 is equal to probability of y is equal to 1, probability of 1, and 0.5%. For less than 2, just simply this one sum up together, 15%. For 4, we sum up these 3 together, we will get 0.5. For 8, all this one plus this one plus this one, we will get 9. And for 16, all together, you sum up, you will get 1. Right? For example, for 2.7 is something here, right? So we will get 10 plus 5, 15%. For 7.99, it will be this one, right? Less than 8, so it will be 0.5. It's similar to 4. Here is the CDF written out. The CDF will be 0 if y is less than 1. If y is between 1 and 2, it is this one, and so on. So it's like a step function, right? It's a step graph. This is a graph of this CDF that we have here. For x as a discrete random variable, the graph of fx that you can see here will have a jump at every possible value of x and will be flat between them. So you can see here up to this one, then we jump up, then we jump up, then we jump up, then we jump up, and then we jump up here. This is called as a step function. Do you want to get the probability between two values? For example, like for any number like a and b. In this way, we can go probability of x between a and b is equal to fb minus fa minus. This is the largest possible x value that is strictly less than a. The reason for subtracting FA rather than FA only, we do because we want to include PX is equal to A and FB minus FA, which gives us probability of X between A and B. This is a quick trick for range in data analysis. In other words, this proposition shows how to use CDF, like fx that we have. In here, our goal is to find the probability that a discrete random variable x is between a and b. In general, fx between a and b is equal to fb, f minus a minus. This fb is the probability up to b. The probability up to b, right? And this one is just before a, just before a, means a is not included. So if x only takes integers and a and b are integers, it becomes probability of x is equal to a is equal to probability of fa minus fa minus 1. And in this case, we can cover x is equal to a to b. Setting a is equal to b gives probability of x is equal to a is equal to probability of A minus probability of A minus 1 and the probability of exact A. It's a quick way to compute probabilities. Let X be the number of days of sick leave taken by a randomly selected employee of a large company during a particular year. If the maximum number of allowable sick days is 14, possible values of X are 0, 1, 2, up to 14. So with F0 is equal to 0.58, F1 is 0.72, and so on to F5. For X, like sick days from 0 to 14, given F0 is equal to 0.58 and so on, then we can calculate probability of X between 2 and 5 is equal to probability of 2, 3, 4, and 5, right? Is equal to probability of 5 minus probability of 1, right? Just B for 2. B for 2, so we can get 22, right? And probability of X is equal to 3 is equal to probability of F3 minus probability of 2, right? So you get 0.05, right? In this way, we can calculate it. The expected value that we show by AX is the average outcome if you repeat an experiment tons of times. So we write EX or mu X is equal to X in D, X multiply PX. Consider a university having 15,000 students. X is equal to number of courses for which a randomly selected student is registered. The PMF of a student is here, right? X, PX, and number of registered students. PMF, number of registered students, up to here. So in order to calculate EX, very easy. 1 multiply probability of this one. 2 plus 2 multiply P2. Up to 7 multiply 7. So 1 multiply 1.01, 2, and up to here you get the same. Or simply you can multiply this one by this one, plus this one multiply this one, plus this one multiply this one, up to here. Up to this one, and you sum up them together, you can get the expected value. We have a proposition here. Sometimes interest will focus on the expected values of some function like hx rather just ex. So in this case, what if we transform x with a function like hx? Then the expected value will be sum of the hx multiply px. That is, this ehx is computed in the same way that ex itself is, except hx is substituted in place of the x that we had. Example here, a store buys 3 computers with a certain type at 500 piece. It will sell them 1,000 apiece. The manufacturer has agreed to purchase any of computers still unsold after a specific period at 200 apiece. If X is the number of computers sold, then we want to go for profit. Profit is, so we say, for example, P0 is 0.1, P1 is 0.2, P2 is 0.3, and P3 is 0.4. So in here, hx is a function and it's a profit. So revenue minus cost is 1,000 plus 200, 3 minus x, minus 1,500, which give us 800x minus 900, right? This is simply the profit. We want to calculate the average profit of this computer store, right? EHX is equal to H0 multiply P0, H1 multiplies P1, H2 multiply P2, H3 multiply P3. Then, how to calculate the H0, right? H0 is based on deviation, revenue minus cost, right? Based on this equation for the profit calculation. We say here 900 minus 900. How? In this case, the guy did not sell any of computers. So how much he bought? He bought 1,500 he paid, right? And because he didn't sell any of them, when he returned, he will get only 600. So 600 and he paid 15, right? So he lost 900. Multiply zero point 0.1. Then in the case that he can sell one computer, if he sell one computer, he can earn 1,000. How much he paid? 1,500, right? He can earn 1,000, and also when he return, he will get 400 because two computers he will return, so he will get 200. He paid 1,500, but he earned 1,400, so he lost minus 100, right? Multiply 2. And then in here we say if he can sell two computers. So he paid 1,500, he earned 2,000, and also 200 when he returned back, right? So these two minus this one, so 700 revenue. But when he sell all three computers, he can earn 3,000. So he paid 1,500 and he can earn 3,000. So 3,000 minus 1,500. So in general, if you sum up them together, on average, he can earn $700. The hx function of interest is quite frequently a linear function, and linear function we say ax plus b, where a is slope and b is intercept. In this case, EHX is easily computed from EX. So if you scale and shift X, the expected value will be EX plus B is equal to E dot EX, A dot EX plus B. To paraphrase, the expected value of a linear function equals the linear function evaluated at the expected value of EX. So let's have PMF as Px and expected value as mu. So then here we want to calculate variance. We can write Vx or sigma to x, right? It's simply this x minus mu. It means the distance between each value and average, right? X minus mu average square multiply px probability, which is equal to ex minus mu. And standard deviation is square root of variance. So the Vx is how much x varies from its mean. And standard deviation is the root square of variance, and it tells us the typical distance from mu. So standard deviation is nice because it's in the same units as x, making it easier to understand compared to variance. Let's see one example here. A library has an upper limit of 6 on the number of videos that can be checked out to an individual at a time. Consider only those who checked out videos and let X denote the number of videos checked out to a library selected individual. Then we have PMF here. So for 1, 30% to 25%, 3, and something like that. So we can calculate mu like this. So if you multiply this one plus these two multiply plus these two multiply plus these two multiply plus these two multiply plus these two multiply, then you can get 2.85. Then we want to calculate Vx variance or sigma square is x each time minus 2.85. It means 1 minus 2.85 square multiply 30. 1 minus 2.85 square multiply 0.3. 2 minus 2.85 square multiply 0.25. Up to the last one, 6 minus 2.85 square multiply 0.5, which will give you this one. And the standard deviation is simply root square of variance, which is 1.8. We already know that the probability distribution for discrete random variables describes how probabilities are assigned to the countable outcome of a random variable. So here we have types of probability distribution for discrete random variables. The first one is Bernoulli distribution. This is one trial, success or failure. Then we have binomial distribution, counting success in fixed trials. Then we have geometric distribution, trials until first success. Then we have negative binomial, trials until R success. Then we have Poisson distribution, events in time or space. We have uniform distribution, where we have equal chances for all outcomes. Then we have hypergeometrics, sampling without replacement. So in the next lectures, we will study them one by one. So here, let's see some practical example. For example, a standard die is rolled. The probability of landing on any face is proportional to the square of the number we obtain, right? And in here, we want to find the probability distribution. So if x is the number on the face of the die, then we write the probability of x equal to x is proportional, this is proportional to x squared. The probability of x taking the value of small x is proportional to x squared. We determine the probability distribution by normalizing the probabilities. So we compute the sum of squares. What is the sample space? 1, 2, 3, 4, 5, 6. And how we can do it? 1 square plus 2 square plus 3 square plus 4 square plus 5 square plus 6 square is equal to 91. So k is equal to 1 by 91. Then we can write x face value, the outcome, x value is equal to px is equal to small x. So for 1, it's 1 by 91. For 2 is 4 by 91. For 3 is 9 by 91. For 4 is 16 by 91. For 5 is equal to 25 by 91, and for 6 is equal to 36 by 91. And if you sum up them together, it means 1 plus 4 plus 9 plus 16 plus 25 plus 36 divided by 91, you will get 91 by 91, which is equal to 1. This confirms the distribution is valid. What is the expectation when a standard unbiased die is rolled? When we say unbiased, it means equal probability. So again, we have 1, 2, 3, 4, 5, and 6. And the probability is equal. It means 1 by 6. Let x indicate the outcome of the experiment. So we say p x is equal to x is always 1 by 6. So p x is equal to 1 is 1 by 6. Same, p x equal to p x equal to 3, p x equal to 4, p x equal to 5, and p x equal to 6. Same, all together, right? Then the expectation ex is equal to sum of x dot px is equal to x, right? So ex is equal to 1 multiply 1 by 6 plus 2 multiply 1 by 6 plus 3 multiply 1 by 6 plus 4 multiply 1 by 6 plus 5 multiply 1 by 6 plus 6 multiply 1 by 6, right? And you will get 7 divided by 2, which is equal to 3.5. This expected value kind of intuitively makes sense because 3.5 is in half a way in between all possible values in a die. Thus, this is the value that you could expect. Next example, if I roll two dice and observe two random variables like x and y. So in here, we have s for x is equal to s for y, which is equal to 1, 2, 3, 4, 5, and 6, right? Assuming the dice are fair, it means all values are equally likely. Then we say px k is equal to 1 by 6 for k is equal to 1, 2, 3, 4, 5, 6, and 0 for otherwise. And similarly, for the same thing for y, we can write, right? So for the same thing for p, y, and k. Next, we want to find out probability of x is equal to 2 and y is equal to 6, right? So, because they are independent random variables, we can write probability of x is equal to 2 and probability of y is equal to 6 is equal to probability of x is equal to 2 multiply probability of x, capital X, is equal to 6. So it is 1 by 6 multiply 1 by 6 is equal to 1 by 36. So next, we want to find out probability of x greater than 3 given y is equal to 2, right? In this case, because x and y are independent, then we can write probability of px greater than 3 given y is equal to simply probability of x greater than 3, which is equal to probability of x is equal to 4 plus probability of x is equal to 5 plus probability of x is equal to 6, right? So 1 by 6 plus 1 by 6 plus 1 by 6 is equal to 1 by 2. And then if we have z is equal to x plus y, we want to find PMF for z. So when we say x plus y, it means the outcome of x plus the outcome of y, right? So sz is equal to what? 2, 3, 4, up to 12. It means this is sum of the outcome of two die, right? So pz2 is equal to pz is equal to 2, which is equal to px is equal to 1 and y is equal to 1. So because they are independent, we can say 1 by 6 multiply 1 by 6 is 1 by 36. For p, z equal to 3 is equal to p z is equal to 3, which is px is equal to 1 or y is equal to 2 plus p x is equal to 2 and y is equal to 1, right? So it means one of them is x is 1, y is 2, or x is 2, y is 1, right? So again, you can say 1 by 6. So this one will be, because they are independent, this will be px multiply py, right? So 1 by 6 multiply 1 by 6 plus 1 by 6 multiply 1 by 6, which give you 1 by 18, right? Then for pz4, we have pz equal to 4 is equal to p x equal to 1, y is equal to 3. Or both of them are 2, x is equal to 2, y is equal to 2. Or p of x is equal to 3 or y is equal to 1, right? So it will be 3 dot 3 multiply 1 by 36 is equal to 1 by 12. In the same way, pz5 is equal to 1 by 9, PZ6 equals to 5 by 36 and up to PZ12 is equal to 1 by 36. And the last one, we want to find out P x is equal to 4, z is equal to 8. P z x is equal to 4 given z is equal to 8, right? So this one is simply equal to probability of x is equal to 4 and z is equal to 8 divided by probability of z equals 8, right? This one is equal to probability of x equal to 4 and y is equal to 4 because this is one of them, right? So when this is 4, the other one is also 4. So y is equal to 4 divided by probability of z is equal to 8. So when z is equal to 8, we have some other cases like 3 and 5, 5 and 3, based on this equation that we have calculated here. So then we can say that x and y are independent. So for this one will be 1 by 6 multiply 1 by 6 and p of z equal to 8 is 5 by 36, which give you 1 by 5, right? The point is here that if x is equal to 4, y is also equal to 4 because z is equal to x plus y, right? So if x is equal to z, then in one case only y will be 4. We want to find the mean of the distance random variable x whose probability is in this table. For example, we have a table like this. We have x and we have px. For example, for -2, it is 0.21. For 1, it is 0.34. For 2, it's 0.24. And for 3.5, it is 0.21, right? So based on the equation that we have, mu is equal to simply sum of x px, right, which is equal to -2 multiply 0.21 plus 1 multiply 0.34 plus 2 multiply 0.24 plus 3.5 multiply 0.21. And if you do that, you will get 1.135. And the last example is here. Suppose we have a discrete random variable like x, and it has a probability distribution like here. For example, x, and we have here px. So for -1, it's 0.2. For 0 is 0.5. For 1, we don't know how much is it. And for 4, it's 0.1. So in here, we want to find out A. Since all probabilities must add up to 1. So all should be equal to 1. So 0.2 plus 0.5 plus A plus 0.1 must be equal to 1, right? So A equals to 1 minus 0.2 plus 0.5 plus 0.1, and in here a is equal to 0.2. Then we want to find out probability of 0, p0. So from the table, simply we can get probability of p0, which is equal to 0.5, right? And we want to find out probability of px greater than 0, which is equal to probability of 1 plus probability of 4, right? Which is equal to, we find probability of 1 here as 0.2 plus 0.1, which is equal to 0.3. Then we want to find out probability of px greater than or equal to 0. So in this case, this one will be also there. So it will be probability of p0 plus probability of p1 plus probability of p4, which is equal to 0.5 plus 0.2 plus 0.1, which is equal to 0.8. probability of px less than or equal to minus 2. We don't have anything here, so it will be 0. The mean of x, right? So mu is equal to sum of x px, which is equal to minus 1 multiply 0.2 plus 0 multiply 0.5 plus 1 multiply 0.2 plus 4 multiply 0.1, and which will give us 0.4, right? The variance, so variance we show by sigma square. Sigma square is sum of x minus mu square px, right? So what is the average? 0.4. So each one minus 0.4. So here we can say this variance is equal to minus 1 minus 0.4 square multiply 0.2 plus second one 0 minus 0.4 square multiply 0.5 plus 1 minus 0.4 square multiply 0.2, we find it here, right? Plus 4 minus 0.4 square multiply 0.1. If you sum up them together, you will get 1.84. And standard deviation, so if this is variance, the standard deviation is simply root square of sigma square, which is equal to root square of 1.84, which is simply equal to 1.3565. So in this case, we calculated A, P0, P greater than 0, P greater than or equal to 0, P less than or equal to minus 2, mean, find mean, variance, and standard deviation here. In summary, what are discrete random variables? A discrete random variable is a type of random variable that can only take on a finite or countably infinite number of values. What is probability distribution? It's a function that describes the likelihood of different outcome in a random event. Expected values, they are the measure of the central tendency of a random variable, which is nothing but the weighted average of the variables where probability is the weight. For variance, variance is the measure of the spread or dispersion of a random variable. Standard deviation is just simply a square root of variance. Thank you so much for your attention. Please feel free to send me your questions, comments, concerns by leaving a comment below this video. Thank you and see you in the next lecture about probability distributions for discrete random variables.